Hello, my name is Dimuthu. I'm from School of Computing, DePaul University, USA. I'm going to talk about our work on hybrid soft robot design. Okay, first the motivation. We know there are many soft robot designs. One of the issues with soft robot is being not able to design them to handle higher payloads. So that means soft robots should be able to control its stiffness on demand. Here we focus on a pneumatic muscle actuated class of soft robots. Their common philosophy is keep increasing the pressure so that stiffness is increased, but stiffness is coupled to bending shape. So we look at a pneumatic muscle actuated soft robot with independent stiffness and shape control design. Let's look at the bio inspiration. Our soap robot design is inspired by the tails of spider monkeys. So these tails are highly adaptable, so they can function at various forms. So, for example, one time the tail can act as a manipulator, and in another occasion, maybe tail can act as a supporting structure. So here, what happened is the tail's muscular lining actuates the underneath skeletal structure. That means the backbone to obtain the desired structural shape and stiffness during these various tasks upon the blood pressure. So, inspired by this structure, we incorporate pneumatic muscle actuators into a rigid backbone to design our soft robot. Similar to this biological phenomena, so we supply pneumatic pressure and the pneumatic muscle actuators, uh, which are located underneath the backbone, uh, change the robot shape and stiffness. Let's look at hybrid soft robot design. Uh, now, this is a soft module. So we incorporated these pneumatic muscle actuators to a rigid backbone. So this is a kind of length constraining mechanism. So it's a fixed length unit. So we uh, inserted three pneumatic muscle actuators into these three rigid chambers, one, two, three, and constrain them using various 3D printed units. So this backbone limits the overall axial extension of the soap robot. Now, next experimental validation. Uh, Here we designed two robot units in the left, one without backbone in the right, our proposed robot design, and we apply a load profile, and that means a torque profile, and record the stiffness. Here we see that the backbone integrated unit has kind of 100% stiffness increase than backbone free unit, this one. By the way, these two modules have identical physical dimensions. uh, Next, we conduct an experiment to establish relationships between supply pressure, stiffness, and bending to prove the independent stiffness and shape controllability. And finally, we present an application example, like we use three of these units and fabricate a tri-fingered gripper and continue with some testing and show that our hybrid robot design can independently control the shape and stiffness. So the final conclusion is this hybrid soap robot design has 100% stiffness increase than backbone free unit, and also it can independently control the stiffness and the shape. Thank you.